So because the concept of structs is so fundamental to Swift programming and object-oriented programming in general, I'm going to give you an example from a different domain. So let's leave the world of medical records for a moment, and we're going to go into the world of graphics and 3D programming. So without knowing a whole lot about this fake program just yet, we do know that it's going to be in 3D, and therefore it's going to want to have some notion of coordinates. So let's create a type called point, where the point is a point in 3D space. Okay. So for this, we're going to want to have an x, a y, and a z. All those will be numerical values. And then for kicks, let's throw in a label as well, just because that could be useful at some point. So in Swift, all we do is say struct point var x int var y int var z int var label string. And voila, there it is. Now at this point from our previous lectures, we know that there's a default member-wise initializer that's created for us already. Okay, and so we're free to use that. Now, what do we want to actually add to this very basic struct? Let's add in a display function, first of all, that prints out the internals of a given point in a nicely formatted way. So, say we have func display, does not return anything. And inside it, we want to say print line and refer to the label, colon, and then show all those internals. Okay, so now if we create our point, we're going to use this default initializer. And notice that for this default initializer, we actually need to supply the first argument name. In general, you don't need to for most methods, but for certain methods you do in Swift, and this is one of them. For initializers, you actually have to specify even the first method argument. So, first method argument name, yes. So let's go ahead and set these to some fictitious values. And for label, let's just call this point I. And so there we go, that's our first struct. And then to display this struct, all we have to do is type in p.display. And so in the console, we see a really nicely formatted output. Shows you the label, colon, and then sort of a typical or textbook display of the 3D coordinate. Okay, so it's very useful, tiny bit of code that we can reuse again and again for all our different points, whatever we might store. Now notice that we created this as a member method, member function. Now we could also create the same function as a type method. Okay, how would we do that? Well, first we've got to take static, add that to the front. And now that it's a type method, we're not immediately associated with any actual instance of point anymore. So we're going to have to pass that in. Okay. So we're going to pass that into display. And now inside our code, we're going to have to refer to that instance P. Good, no errors there. And then finally, in the way we call it, it's going to be different, right? Because instead of referring to a particular object, we now refer to the class point dot display, and then we pass in P. And notice we don't pass in the argument name, because by default, for most method situations, you don't need to pass in the first argument. Okay. Great, and sure enough, the output is the same, okay, which is what we want. Same function, just done as a type method instead of instance method. Now, why would we want to choose one over the other? Well, it just saves some typing. Because we're only dealing with one object in this function, I prefer to make it a instance method. Saves you some typing. But the argument can be made that since it's kind of a utility class, that you would make it a type function instead, type method. So up to you. It's just good to know the way you would do both and the differences between them right now. Okay, so let's add another function. What about translation? Let's say we wanted to be able to take a given point and move it around in space by some fixed amount. So func translate, and we want to pass in offset in x direction, offset y, offset z, and we don't return anything. Instead, we want to modify the values inside our point instance. Uh-oh. Look at these three errors screaming back at us. What's going on? Okay, error. Binary operator plus equals cannot be applied to two int operands. Well, really? X plus equals offset x. We've done code just like this before in other chapters. What's wrong? Well, turns out that there's a wrench. And the wrench is that by default, methods cannot alter their properties. Okay, and this is just done as a software sort of a protection, if you will. Just like there's like read-only mode, you know, with certain files or in database records. Often that's a default setting, just so that you don't muck up the data yourself. And kind of in a very similar design choice, Swift has made struct properties read-only by default. That means if you want to actually change something, you're going to have to add a certain keyword to the method that's changing something. And so all we have to do is type in mutating. Okay, this will signal to Swift that, okay, in this function, I know I'm doing something that's potentially dangerous, which is I am modifying some aspect of my instance. And so there you go. That's all you need. And then the XYZ will be modified accordingly. So let's test this function. So we've displayed the point as originally created. Now we can translate that point by some amount. Just shift everything over by 1. And then let's display that same point again. Beautiful. Everything works. So you can imagine a whole host of very useful functions that you can make, either type methods or instance methods. And the beauty is that this code is all contained inside this point struct. It's hidden away from all your other files, all your other code, and your other code just has to know how to call these functions. Just like we've made use of so much functionality without getting to all the messy details, we just have to know what function to call, what the inputs are, what the effects of that function are, and what the outputs are. And so this is a concept known as encapsulation inside object-oriented programming. And it's a way of managing complexity over large projects and large code bases. Because even though our code base is very, very small, the reality is we could be using a much larger, in fact, we are using a much larger code base. This print line, for instance, hides a great deal of complexity underneath the hood. And with the other short examples we've written, there's been a lot under the hood as well. So just a thought to keep in mind, why things are the way they are has often a lot to do with managing and hiding complexity in this kind of way. And structs are one step towards making this kind of complexity hiding possible.